So what we're going to do today is a little too loud. What we're going to do today is we're going to start talking about the thymus. The thymus is one of the lymphoid tissues that we didn't get to yesterday, and it functions in a different way. The thymus, rather than protecting us directly from one pathogen or another, the thymus now is functioning within the immune system to select a particular kind of immune cell called a T lymphocyte. In fact, the T stands for the thymus. And we'll start today by describing something known as positive and negative T cell selection in the thymus. Now, when we produce these so-called naive T lymphocytes, this happens even during development, even in utero, these cells leave the red bone marrow and go out into the blood vascular compartment, but they don't stay there. Instead, they settle into this structure called the thymus. As I mentioned yesterday, the thymus is really robust in young animals. And even in humans, by the time we reach puberty, it's pretty much gone. But what the thymus does is it plays a role in selecting for T lymphocytes. And it has two kinds of selection. One type of selection, said to be positive selection, is T lymphocyte. Can you recognize a foreign protein? That's the positive selection, if they can. The other kind of selection is said to be negative selection. And the negative selection is, can you recognize proteins that belong to us? Can you recognize self-proteins? That's dangerous. They can recognize our own proteins because many of these T lymphocytes are going to be T killer cells, and they're going to have mechanisms to kill cells. And so we don't want to be having these T lymphocytes escape the thymus and have the ability to kill any number of our own cells. So we have to make these selections, and we'll talk a little bit about how that gets done. I'm going to simplify this way down. I'm going to anthropomorphize it a whole bunch. But if you begin to look at the literature, you recognize that all the molecular details are all sorted out. We know all of the molecules that are involved here, and we know how all these molecules interact and how it really works. But the immunologists are going to roll their eyes when I tell this story. The innate immune system, then we're going to talk about the innate immune system and introduction to the adaptive immunity. When we think about the immune system, we divide it into these two big camps. One is said to be the innate or non-specific immune system, and the other is said to be the adaptive or specific immune system. We're going to work our way through the non-specific or innate immune system first. And when we start talking about the innate immune system, we mean it's non-specific. So that means what we find is that it's not highly targeted. When we get to the adaptive immune system, we'll see that immune system is targeting relatively short series of amino acids and proteins, 16 to 20 amino acids. But the advantage of the non-specific or innate immune system is that it has a rapid response. This will gear up in a matter of a few hours. It's not highly targeted, and because it's not highly targeted, it tends to be destructive. So it's going to do a lot of damage. But its function is to be a kind of short-term holding action against the pathogens. So it's fighting off the pathogens until the adaptive immune system can engage and specifically attack those pathogens. There are a group of cells that we'll talk about briefly when we talk about the innate immune system. And these are so-called granulocytes. This term granulocyte is left over from the 19th century because when the 19th century histologists looked at blood cells, they saw this subset of cells in the blood that were chock full of these granules. We now know these are vesicles. And the granules then could stain differently, or these cells could stain differently. Sometimes they stained with neutral dyes, these are the neutrophils. Sometimes they stained with a specific kind of dye called eosin, these are eosinophils. And sometimes they stained with basic dyes that had a basic pH, and those are basophils. We're going to lump them together and call them granulocytes, and most of our time is going to be spent on the neutrophils. We're going to divide our innate immune response into two big categories. We're going to talk about the response to viruses, and we're going to tell the story of our innate response to viruses in terms of interferon. And I'll tell this story in terms of the COVID virus. And then there'll be an innate response to bacteria, and we're going to call this inflammation, and we'll work our way through this too. The signs of inflammation have been known literally for centuries. Galen developed the ideas of inflammation when he was a physician in, I think it was the 1st or 2nd century AD, of the current era, when he was a physician for gladiators in Anatolia. And so he was seeing lots of inflammation. And he coined several terms for these signs, and he didn't know what caused it. We now have a pretty good idea of what's causing each of the signs, and we'll see if there's time to work our way through that. Then we start to think about adaptive immunity. And adaptive immunity is what we normally think about when we think about the immune system. It's the adaptive immune system, which is highly targeted to a particular pathogen. Not only is it highly targeted to a particular pathogen, it's highly targeted to an amino acid sequence on that pathogen or the proteins that pathogen produces. But the adaptive immune response is slow. Its initial response is really slow, and we'll see that it's slow probably on Monday. We see that it's slow because it all begins as a single cell. It's initiated by a single naive cell, and that cell has to proliferate and make thousands of copies of itself. And each of those thousands of copies have to make the same antibody. So that takes time. So it takes, up to 2 weeks to get a decent adaptive immune response. But in contrast to the innate immune response, the adaptive immune response is highly targeted. It's those antibodies, whether it's going to be T cell receptors in the T cell system or secreted antibodies in the B cell system. Those, if you put your phone away, I'd appreciate it. Those antibodies now are going to, I'll wait until you're finished. So these antibodies now are going to target a 16 to 20 amino acid sequence in the target proteins. So if you have a bacterium or a virus, these antibodies are going to target relatively short sequences of amino acids. So it's highly specific. The other thing that's different here in the adaptive immune response from the innate immune response is that it has memory. If things are working right, then your immune system can recognize those pathogens for years. Again, we're better at having this memory when we're younger than when we're older, but we still have some memory here, and we'll talk about how that memory is done. When we talk about the adaptive immune response, we break it into these two branches. One is said to be the humoral branch, and the other is said to be the cellular branch. Whenever you see the term humoral branch, humoral means it's out in the humerus, it's in the fluids. And in the humoral branch, we have B lymphocytes. And those B lymphocytes now are secreting antibodies that are now going to attach to antigens that are in the extracellular space, so in the extracellular environment. The cellular branch is different. The cellular branch uses cells called T lymphocytes. And these T lymphocytes recognize foreign proteins that are displayed on other cells. So again, in the humoral branch, B lymphocytes secrete antibodies that recognize foreign proteins, antigens, that are out and about extracellularly. But the cellular branch needs to work through cell-cell contact. And the cell-cell contact is from T lymphocytes contacting antigen fragments of these foreign proteins expressed in other cells. And by Monday, we'll go through that. But let's start out with this simplified story of thymus. Let's do it this way. The thymus and T lymphocyte selection. We'll start out here in the red bone marrow. As all cells of the immune system begin as hematopoietic stem cells in the red bone marrow. So we're out here in the red bone marrow. This happens to be a long bone. And these cells, these hematopoietic stem cells, produce all manner of immune cells. But the ones we're going to talk about now are so-called naive T lymphocytes. Much of this happens early in development. There's some indication this is happening in utero and then continues on for the first years of life. This story, we think the thymus is pretty much exhausted by the time you reach puberty. But the story is that these T lymphocytes are produced in the red bone marrow. And then they enter the blood vascular compartment, and they find their way to this structure. I'm going to put it as a box. And this is the thymus. Anatomically, the thymus is located sort of around the upper thoracic region. And when in the thymus, we have a whole series of epithelial cells. Draw these as kind of ovals. And I'm going to label these as thymic epithelial cells. Sometimes you'll see these referred to as stromal epithelial cells. The function of these epithelial cells, what they do for a living, is they select. I can do it this way. They positively and negatively select for T lymphocytes. The first thing that happens is that one of these orange naive T lymphocytes finds its way into the thymus, and it binds to one of these stromal epithelial cells. Now, if you get down into the weeds of this, you'll find that the thymus is divided into regions. There's a cortical region, there's a medullary region, and in truth, we're going to do some selection in the cortical region and some selection in the medullary region. But I'm going to simplify that. I'm going to say it's all done in one story here. So the idea here is that this naive T lymphocyte arrives on this epithelial cell. And the epithelial cell greets the T lymphocyte. And they say hello. There's a handshake. And then this epithelial cell asks a question, molecularly, of course, but it asks the question of this naive T lymphocyte. Can you recognize proteins? Can you recognize proteins expressed on other cells? And if this cell says, no, I'm not very good at that. I'm not very good at recognizing proteins expressed in other cells. Then this epithelial cell says, T cell, you're useless, go die. And it turns on a series of genes because it withholds growth factors. This epithelial cell withholds growth factors, and this cell will undergo its apoptotic machinery, and it will just quietly die. But if this T cell arrives, another T cell arrives, there's a handshake, and the epithelial cell, the stromal epithelial cell, asks the T cell, can you recognize proteins expressed on other cells? And this orange T lymphocyte says, sure, I have the machinery to do that. I can recognize proteins on other cells. And this cell basically says, congratulations, and passes that cell on to another cell. This cell says, well, congratulations, you've graduated from school where you now can recognize foreign proteins, but now tell me, what kind of proteins can you recognize? And so this cell then begins exposing this naive T lymphocyte to all manner of self-proteins, all manner of proteins we express on our cells throughout our bodies. And if this cell says, doesn't matter what you throw at me, I'm going to recognize it, then this stromal epithelial cell says to this naive T lymphocyte, it says, you're dangerous, go die, and withholds growth factors and induces the apoptotic machinery. This cell will be passed from cell to cell to cell, and each cell will have different proteins on its surface, testing whether or not this naive T cell can recognize those proteins. And those proteins are a whole panoply of proteins that are expressed in cells throughout our body. And to pass through this gauntlet and come out the other side, this T cell has to be capable of two things. It has to have been selected positively, because it can select protein. But simultaneously, as it's moving through the system, it also has to be selected negatively in the sense that it does not recognize our own proteins. This is important because if we turn out T lymphocytes, many of which are going to be so-called cytotoxic T killer cells, if we turn out these T lymphocytes that recognize our own proteins, they're going to be killing our own cells. This is an autoimmune disease, and we do it often enough. It looks like type 1 diabetes is a kind of autoimmune disease where our immune system begins to recognize the beta cells on our pancreas as foreign and kills those cells so we can no longer make insulin, and we have to inject insulin. There are other diseases which seem to approach the central nervous system, and T cells will be killing oligodendrocytes in the central nervous system, and there you begin to see signs of multiple sclerosis. There are a whole variety of autoimmune diseases where our immune system screws up and begins to recognize our own proteins as foreign, our own cells as foreign, and kills those cells. So you want to be careful during development in the early stages of the functioning of the thymus that you select for T cells that are useful but are not indiscriminate. And that's what this thing is. This whole series is to select positively for T cells that recognize proteins, but also select negatively in the sense that these T cells won't recognize our own proteins. And that's what these things do. And the molecular machine for this is exquisite. It's beautiful. If you want to read some reviews on it, you can find it pretty quickly. Yes?
If you have damage to your thymus, does the whole situation run amok? What happens?
So if you have damage to the thymus, there are cases of that. There's a situation during the development. There are a series of pharyngeal pouches that form. And there's one pouch called the third pharyngeal pouch. And rarely, in some individuals, the third pharyngeal pouch doesn't develop. And that pharyngeal pouch is destined to become the thymus. Those individuals don't have a thymus, and they can't do this job. Okay. There are other cases where the T lymphocytes lack the right machinery to put what we're going to see are alpha and beta subunits, which are part of the T cell receptors, onto the surface.
Okay.
And so there are two ways you can not get a T cell response. One is not to have a thymus, and the other is to have defective T cells. And both of those are possible. Okay. Anything else? Yeah?
Which one is the positive, which one is the negative selection?
Okay, which one is positive, which one is negative? The positive selection is, yes, you can see proteins. That means that's a problem. Well, no, I'm sorry. The positive one is, yes, you can see proteins. That's a minimum requirement. So we say, yes, that was a positive development. You can recognize proteins. The negative selection is to make sure these T lymphocytes don't recognize our own proteins. So the first selection is positive or negative, plus minus, let's do plus minus, in the sense that either it can recognize proteins or it can't. If it can't, it's rejected. If it can, then it goes on to be looked at by all these other stromal epithelial cells. And the question at each step is, can you recognize our own proteins? And if you can, you're a problem, and you can't escape the thymus. And that's the negative selection. Okay. Anything else? Okay. Well, that's the thymus story. That brings us to the end of the lymphoid tissues. So now we can begin to think about the adaptive and innate immune responses. We'll divide the adaptive immune response into these two categories. The adaptive immune response is going to be divided into the cellular branch And the adaptive immune response of the cellular branch, that's all taken care of by the T lymphocytes. These are the cells that we just talked about being selected for in the thymus. The other branch of the adaptive immune response is called the Immoral Branch. And the Immoral Branch functions through cells that are called B lymphocytes. You just have to remember they're B lymphocytes. There's no logic to it. It turns out the way they were developed is they were first found in an outpocketing of chickens. This was called the bursa fabrica, and so it's left with the B cells. So there's a detail if it helps remember it. But B cells now are part of the Immoral Branch, and what the B cells do is they secrete antibodies. And the antibodies bind selectively to antigen to form an antigen antibody complex. We'll talk more about that later. But the major idea here, what I want you to really hold on to, is when you see this B cell lineage, B cell idea, for the most part, think that these are secreting antibodies, and those antibodies are going to be binding to foreign proteins out and about in the extracellular space. Put that in one bucket. Over here on the cellular branch, we have T lymphocytes. We'll see that these lymphocytes can be either T killer cells. Sometimes you'll see this referred to as cytotoxic T killer cells and T helper cells. The T killer cells and the T helper cells, these guys, whether one or the other, these express something known as T cell receptors. And the T cell receptors recognize foreign proteins expressed as antigen fragments. On proteins of other cells. So for the T cell response to be effective, there has to be cell-cell contact. So hold on to that idea, and we'll come back to it on Monday. We have to have cell-cell contact for these T cell receptors to be effective. The players here are a T cell receptor on either T helper cells or T killer cells. That's kind of the T cell receptor is the protein that's going to recognize foreign proteins. But to recognize those foreign proteins, those proteins can't be floating about. They have to be expressed and displayed on particular proteins of other cells, and we'll walk our way through that on Monday. So those are the two big categories of the adaptive immune response. Now, over here, we have the innate immune response. And I'm going to divide the innate immune response into a response, do it this way, to viruses. And we're going to call this interferon. And then the innate immune response, the other pattern here, is going to be a response to bacteria. And this is said to be inflammation. So what we've done here is we've broken down our immune system into an adaptive branch and an innate branch. We further subdivided the adaptive branch into the Immoral Branch, which is secreted antibodies, and the cellular branch, which uses T lymphocytes that have passed through the thymus, and in this case, there has to be cell-cell contact. The innate response is going to be divided into interferon, and there are others here. There are a bunch of others, but I want to tell you the story of interferon for viruses and the response to inflammation in terms of bacteria. This one we're all aware of. We've all had a splinter under skin, and we get that inflammatory response and go through that. This one we're not so familiar with. It happens pretty much in the background. Whenever we get exposed to a virus, and it's a novel virus, we start this interferon response. And again, when you think about the innate immune response, it's fast, it's not highly targeted, and it's often destructive. So hold that in mind when we talk about this response to pathogens in terms of bacteria for inflammation and in terms of interferon for viruses. Or inflammation, yeah, inflammation for bacteria, viruses, interferon. So the first story here is going to be interferon and the response to viruses. Since we're still in the midst of a pandemic, I may as well use the example of the SARS CoV-2 virus. This, of course, is the virus that causes COVID. It's a respiratory virus. It's going to attach to epithelial cells in our respiratory tract. It's going to attach to it's going to attach to cells all along our respiratory tract, in our nose and our throat, all the way down into our lungs. But the story is pretty much the same. We have this series of epithelial cells. As an epithelium, this sits on a basal lamina. So this is the outside world. This could be the opening of your pharynx, could be the opening of your nose, and these are the epithelial cells lining it. Could be all the way down into your lung. And then there are these viruses. This is a coronavirus. Specifically, it's a SARS-CoV-2 coronavirus. The SARS-CoV-2 coronavirus gets its name as a coronavirus is that it has these spikes sticking out all over it. This is said to be the spike protein. Sometimes you'll see it maybe abbreviated just as the S protein. The spike protein is this spike which can bind to a molecule on the surface of the epithelial cells. So on the surface of the epithelial cell, this is going to be a protein. This is called ACE2. We're going to run into ACE1 later when we talk about the kidney. But this is the full name is angiotensin converting enzyme. There are two varieties of this, ACE1 and ACE2. ACE2 is the one that's found on epithelial cells everywhere. ACE1 is found mostly on cells of the blood vascular system. Regardless, the ACE2 is the receptor for the spike protein. So let me put it over here, make it a little smaller so I can work with it. So here's the ACE2 receptor. Here's the spike protein that's part of the virus. It's got a whole crown of these things. Now, it's a little unclear what happens at this point. There have been a couple of models. In one model, the virus, along with the ACE2 protein, is endocytosed brought into the cell, and everything happens then intracellularly. But we're thinking now, particularly with these most recent variants, because they're much more transmissible, we think now there's another transmembrane protein out here. I'll put this one in orange. So transmembrane protein out here, which has a name called TMPRSS2. Transmembrane protein. Yeah, transmembrane protein, TMPR. Transmembrane protein, active site serine 2. Long-winded. It's a protease. And what this protease does is it breaks the spike protein. More accurately, you'd say it cleaves it. So if we imagine here, this is, put it in red. We imagine here that this is the Sars virus. And it has this spike sticking out of it. This spike is a pretty good sized protein. It's like 1,200 amino acids. And right in the middle of it, there's a juncture called the S1-S2 juncture. And it's this S1-S2 juncture, which is the target for TMPRSS2. It's a protease. So what it does is it clips it. Clips it right there. When it clips this S1-S2 segment, it exposes in this region a series of hydrophobic amino acids. Now again, in the early models, this all happened inside the cell, inside vesicles. We now think in the newer varieties, in the newer variants, the Omicron and the Deltas, that perhaps this is going on the surface. So that now this virus, which has had its clipped spike protein, with the spike protein exposed, with those hydrophobic amino acids exposed, this now gives it an avenue into the cells. The hydrophobic amino acids permit access of the virus into the epithelial cell. Once inside the cell, this virus co-opts the protein synthesis machinery. Of the cell to make viruses. Then we proliferate these viruses, hundreds or thousands of them, and then they now will escape out into the extracellular environment. They can then bind to the transmembrane proteins here, bind to the ACE2 proteins, and start the process in neighboring cells. So this is a multiplying event. Each cell that's infected with a virus may generate thousands of these viruses, and each of those thousands may then infect thousands of other cells. So we get an expanding infection of these viruses. Well, that's really dangerous. And so one of the first things that happens is that when this cell begins to see virus proliferation. This cell responds to that virus proliferation by secreting something known as interferon. Again, the interferon is a molecule, it's a protein that's being released from virus-infected cells. This cell's a goner, there's nothing you can do about it. So what the interferon is doing is the interferon is binding to neighboring cells. And in binding to those neighboring cells, it changes the metabolism of those cells. So in the neighboring cells, the interferon has this effect of reducing endocytosis. It reduces exocytosis. It reduces protein synthesis. So what it's trying to do is it's trying to slow down or stop the proliferation of the viruses. But it does that at a cost, because we're now reducing the ability of these cells to endocytose materials. Cells need to do endocytosis to stay alive. But we're slowing it down because there's this threat in the neighborhood. We slow down exocytosis because this is how the viruses are going to escape from the cells. So we slow that down. And then, even more so, we slow down protein synthesis because these virus-infected cells are making thousands of copies of the virus itself. And they're making thousands of copies of the virus itself by co-opting the protein synthesis machinery of the cell. So if you can suppress the protein synthesis machinery of the cell, then you reduce the number of viruses that are released. Yes?
Why do we have the TMPR protease in our cells if it's functional and allows for the virus to enter the cells?
That protease apparently does a lot of other things. The TMPRSS2 seems to do other things. It's cleaving other molecules to give them better access to the cell. That's my understanding. So it has a real-world function. It's not just there to kill us. And so it does positive things. And it just turns out that these coronaviruses have the ability first to bind to our ACE2 receptors, and then have the ability to have the TMPRSS2 cleave it. I suspect if you look in bats, where this virus seems to be endemic, that there are plenty of ACE2 molecules on their cells and also plenty of TMPRSS2 proteins as well, because those viruses apparently have been in bats for a long time. There are a whole series of coronaviruses that are in bats, and we're basically waiting for them to come out and do serious harm. Now, if you read the literature on this, and I'm just skimming over the surface, what I want you to know about is the interferon, because this is a typical non-specific or innate response to viruses. But if you begin to look at the details of this thing, this virus takes over the cell in so many different ways. It takes over all manner of activities inside the cell, one of which is the production of interferon. So it suppresses interferon production. Yes?
So does the interferon only work in that single epithelial cell, or does it secrete it to the other neighboring cells?
So the interferon is a molecule that's secreted out into the neighborhood on the basolateral side of these epithelial cells, and then it can move from cell to cell. I'm not sure if it can move very far. I don't know. I have not seen anything which says the interferon gets to be bloodborne and acts like a long-distance hormone. I can imagine it could, but I can also imagine it's working locally. So I don't know the details on that. Anything else? Yes?
I've read that you also have ACE2 receptors in neurons. Is that true?
Probably do have some ACE2 receptors in neurons, and it's one of the concerns. if things are working right, presumably these viruses shouldn't get beyond the blood-brain barrier. The endothelial cells in the brain are pretty well tacked together with tight junctions. So hopefully these guys don't get beyond that. But it appears in some cases we do get infections, not only of the epithelial cells, but we get infections of endothelial cells as well, and maybe even myocardial cells. That's why there's a high incidence of myocarditis, where we get infections, we get inflammation of the myocardium. That seems to go along with this disease often, not always, but often. There seems to be some endocarditis, where we get infections of the endothelial cells. And then again, as you're pointing out, if these get beyond the blood-brain barrier, they can bind to neurons. And we don't know what kind of havoc they're playing in the central nervous system. Whether the brain fog, which is part of the symptoms for many people of COVID, whether that's involved with this attack of our central nervous system cells is unclear. It's pretty clear that the attack of these cells on the epithelial cells is the reason why you lose taste and smell. Those are epithelial cells in your olfactory epithelium and on your tongue. And those are epithelial cells. They're susceptible to attack by these viruses. The viruses get in and destroy them, and you lose your sense of taste and smell. Yes?
Since there's no exocytosis or anything like that.
Well, I wouldn't say there's no.
Oh, okay. So, but does the virus stay in the cell, and does it get destroyed in the cell?
In the best of all worlds, under this scenario, those viruses would be contained within that cell. It's almost certainly not true. For one thing, these viruses are going to, part of what they do is they suppress interferon production. And so the interferon is not completely effective in preventing these viruses from getting out, but presumably, hopefully, it slows it down a little bit, so your entire system isn't overwhelmed in a matter of days. Yes?
So the cell has a mechanism for detecting when viruses are inside of it, right?
Right.
Why doesn't it then just immediately do like massive ligase activity or just kill itself and just nuke everything inside of it?
What? I haven't a good answer to that. I suspect that in this arms race between cells and viruses, one of the things these viruses do is they prevent that apoptotic machinery from taking over and killing the cell and preventing further division of the viruses. I mean, I've read this material and it's pretty baroque, but one of the first things that happens when these viruses get into the cells is they then start producing their own proteins. And among those proteins are a variety of proteins, the first ones produced, that go out and basically tell the cell's machinery, we're in charge now. You're not running your own show, we're running the show.
So that literally can't.
I think it literally can't, because the proteins from these viruses have taken over the show. My imagination of this is the Peaky Blinders proteins, when Arthur comes in and says, when they take over one of the gambling operations, and Arthur says, okay guys, we're in charge now, you have nothing to do with this. That's what these proteins are doing. Anything else? Okay. Oh, goodness. That's the interferon story. Let me quickly, on the back board, talk about inflammation. And the inflammation is a response to bacteria. So we can imagine here a splinter being driven into the dermis. So this is the epidermis. Down here is the dermis. Along with these epithelial cells in the epidermis are going to be cells called mast cells. And the mast cells secrete histamine. if we drive a splinter carrying bacteria under the skin, but these are bacteria, we initiate this process called inflammation. And there are these ancient signs of inflammation. The ancient signs of inflammation, called the cardinal signs of inflammation, are redness, swelling, heat, and pain. To this day, medical students, these ideas were first put forth by Galen in the 2nd century AD. And he recognized these signs of inflammation. And to this day, we recognize and teach these signs of inflammation in their original Latin, where this is rubor, tumor, calor, dolor. Has a nice ring to it. Rubor, tumor, calor, dolor. And the story is, you go through these signs of rubor, tumor, calor, dolor, and then you reach the point where you say, I'm never going to get better. This is miserable. It's going to be like this forever, and that's called Eeyore. That's a joke. And with that, I'll let you go.